All right, I think we're recording. I've been meaning to do this forever, but just a million other priorities. Um, this is a demo of my personal Linux distribution called Nest. Um, I want to show off what it can do and why I spend so much time working on it. Um, and I think the best way to do that is to um, set up this brand new single board computer, a Radxa Zero, um, and we're going to do it live. We're going to do it here, um, and we're going to see what happens. I don't know. So let's go. Just gonna tear it open. So funny to me, I have to say, when YouTubers they have these like big ass fucking knives that they just use to open boxes. They just use to open boxes, and they're never good at it because knives are not good at opening stuff. They're good at cutting. You just need this. It's like a little razor blade. I'll get off my soapbox. So new single board computer, always exciting. Here it is, the Radxa Zero. All right, so there it is, and I got an SD card here. I'm gonna build my OS for it. Just go back, get this going in just a second. So the way my so the way this works, the way Nest works is we build a unique image for every node. Um, we recognize that this tiny PC is just not really fast enough to apply all of the customizations that I want to deliver, to build a web service, to build this or that, whatever this thing is going to be doing. This thing's actually going to be a storage node in my Ceph cluster eventually, because it has a nice big eMMC chip here. And this quad core CPU is pretty snappy. It's 1.8 gigahertz and it has 4 gigs of RAM. So it's a pretty capable board, but it is still slower, especially running with the SD card than I would like to install various packages and configurations uniquely live on this board. So we build an image for every node. And we realize a number of benefits from this as well. Faster installation, faster upgrades, the ability to reset images. But we do this all in order to make it reasonable, feasible even to build images for um, dozens of nodes, hundreds potentially. We have to automate it whenever you, especially whenever you want to accomplish a time-consuming task. Well, we don't really need to get into that. We just automate it. Um, and my automation tends to take the form of Git repositories. And that's what we have here. So I have, let's see, um, uh, I moved the terminal out of the way here for this zoom bar. Share, but I'm just doing this in Zoom because it's easy, right? And so I'm looking off to the side. I'm looking at myself in this picture-in-picture window because that's just how I do it. Sorry. But yeah, I got to get this bar out of the way, and so that's just a little configuration in my window manager that adds a little extra gap. It's really convenient, and it persists as I open other windows. That gap remains, and of course I can adjust it per workspace. So here, maybe I want my web browser. I don't care if the Zoom bar is covering my tabs, for example. I'd rather have more web content space. We can do that. But in the terminal, it's cutting off my stuff. So let's go. Make sure I'm on the latest version. It's a good thing I updated there. And in here, I have my automation. And so these are just a set of rules that another server is going to run for me on my behalf, so I don't have to do it. Then down here, I have a bunch of definitions for various types of nodes that I build: infrastructure nodes, server nodes, clusters, workstations. So what does these look like for real? So here's my list of clusters. These are very simple, short little files. And in my case, I am going to want to build one called demo. This is going to run on my ARM 64 builder. It's an ARM 64 chip. And I have builders, actual other nodes like this, whose only job is to build other nodes. I can pass it a few variables. In this case, the hostname, whatever I want. I'm going to call it demo. The profile. This is an important concept of my operating system, where we have a number of profiles. This is a concept that comes from Gentoo, the distribution on which, or the meta distribution on which Nest is based. So if I say you select profile lists, you'll see, for example, all of the Gentoo profiles that are available, including things like, okay, you want to be a desktop with Plasma or a desktop with GNOME. These are essentially pre-canned configurations for the Portage package manager, but I use it for a bunch of other system-related configurations as well. And then down here, you can see my profiles for Nest, including, at least for the Haswell or AMD 64 nodes. These are actually defined in a repository like any other configuration in Nest. And so a full list of these, you can CD bar Nest profiles. Yeah. Desk. All right, so we have a full list of these profiles here, including the ones for ARM 64, which the select is not showing me. So we have profiles for Cortex, A53, and A72. They're different architectures. One's in order execution. The A53, the A72 is out of order. And so I target my compiler optimizations for each of those. Likewise, for AMD 64, Haswell represents the x86 64 v2 spec. There's a new v3 spec, I think, which has, or no, Haswell's v3. There's a new v4 spec, which has AVX 512. And if I had a system that could benefit from that, I would target optimizations for that as well. I also have profiles for ARM 32-bit, Cortex A8, and only one platform on there. That's the BeagleBone Black. But that's the second field here. That's the platform. So we have platforms for, it's an optional field, so you don't have to have a special platform. You can just have a generic Haswell server, generic Haswell workstation. You can have a generic Cortex A53 server. And In that case, it's not going to run on anything because ARM is very platform specific, very platform dependent. But yeah, so this is a Radxa Zero. It's going to be a server. I could make it something else, but that's what I support right now. Right. So the platform, Radxa Zero. You know, I don't even need that because it will be determined from the platform and will that's stupid. All right. This is so complicated, even I forget it sometimes. All right. But other nodes here that I have, my workstations, you can see all the build definitions for these. Here's my change. I'm going to build demo from a template. It's going to run on my ARM64 builder, and it's going to be called demo. It's a Radxa Zero server. Say build demo git push CI. When I push this to my GitLab server, I can pass a variable that says only build this new demo. Then we're not going to build all 20 something nodes that I have currently defined. So let's go back here to GitLab. I'm going to look for stage 3. That's the project. Stage 3 representing the final stage of the build. That's another concept I borrowed from Gentoo. Gentoo is famous for its installation stages, stage 1, 2, and 3. Stage 1 being the one you have to bootstrap your own compiler on. Stage 3 being a basically ready to go image. And I brought that concept here over to Nest. So we have these 3 stages, stage 3, 2, and 1. 3, 2, 1. We also have a stage 0, which is an updated version of Gentoo stage 3. So it goes from, if I were bootstrapping this from scratch, with boot build, it's not important. Ultimately, Nest is self-hosted, and so it doesn't really matter what Gentoo is doing now. I just borrow their package system, package manager. The rest is all mine. It's really a bootstrapping concern that's long gone. 3 stages. Stage 3 being the last stage. You can see here my latest commit, build demo. I can click on this and I can see the code that I wrote, for example. There's my code, there's my definition, and that kicked off a pipeline. What's a pipeline? Well, let's look at it. Pipeline is just a set of jobs. So I can see my my build demo job, and we can follow along with what it's doing. Right here, you can see, for example, that we are starting off from stage 2. So stage 2, we're going to build demo using a stage 2 image that was targeted to that Radxa Zero server profile. And then we're going to do some actual customization to make this an actual specific host. We're going to, give it a machine ID, a host name, Puppet SSL certificates. And we're going to then run Puppet. We're going to run Puppet, and Puppet is going to do everything else. It's going to set some things that I didn't want to set in previous stages because of security reasons, like the root password, Wi-Fi credentials. It's going to actually set up a real host name instead of the one that's temporarily used for building. But we can look at another pipeline and see far more interesting things. Like my previous pipeline here actually built everything. It built all of my nodes, and it did so in 107 minutes. So you think, oh, this is unrealistic to build individual images for all of these nodes. No, it is. It takes a couple of hours. It's not a big deal because you're just applying these small changes to an image that you built previously. In this case, stage two. And so you can actually go back and see the stage two builds here. And you think, okay, well, then that surely is the slow thing. And so let's look at how long that build took. Stage two, 217 minutes to build specific images with kernels for all of these platforms. This is really nothing. This is this is the kind of work that would take a human weeks to do. I do every day, and it just takes hours. And I go skating while it builds. It's not a big deal. All right, so in this case, we're building that Radxa Zero server. And so what did that build do? I can find out. I can interrogate it. Like I can see the build here. Well, it started out in this case um, from my stage one. It makes sense. Stage two starts from stage one, right? Um, it does a few portage setup things, and then it immediately, as soon as possible, calls Puppet, right? We want to do what we want to do in Nest is move as much of the build and automation out of this imperative domain. For example, the container file, the Docker file, you might know it as. I don't use Docker, I use Podman. Um, but yeah, I just want to run Puppet. I don't want to have a list of instructions here. I want to define my configurations. I want to declare them. I want to say this is how it should be and let the tools work it out. That's how it saves me time and effort. Um, it's a bit all over the place, but that's the whole thing. I'm not preparing this all off the cuff. We're just talking. We're chatting about my operating system here. But yeah, so I can go and I can see what was done. Moreover, like it's it's all version controlled. I can see exactly what version of Puppet my Puppet code was applied here. So stage two does things like compiles the kernel. That's the big thing it does, and we let Puppet compile the kernel. Why not? Um, it can do it. It can run. That's what it's good at. It's run it. It's good at defining configurations, running commands, and checking the status, defining relationships between processes. It's all great. Um, but ultimately, what results is a set of images. We can see these in the container registry that GitLab provides. I push all these images up here. So these are full images with debug files and everything, and they're big. That Radxa Zero image, 9 gigs, right? 9 gigs. And like I said, that's the uncompressed size. Compressed is like 4 gigs. It's a lot of text files, data files. Workstations even bigger, 22 gigs. That's the Pinebook workstation. Haswell being complex instruction set architecture has smaller code size, 20 gigs, right? So it's interesting to actually see that difference because they're identically configured. They have the same packages, the same versions, everything, right? It's just a different architecture. Okay. Um, yeah, so for now, I think stage three, it should be getting pretty close to done. It might be um, copying the image over to the final destination now. That's what it is doing. It rsyncs the image, just rsyncs the image over to a file server. And that's where we do everything like installing, updating, and the like. Okay, so I've been talking about Puppet. We want to move as much of this build automation into Puppet as possible. And that's really where Nest lives, is in this repository called Puppet. I can call it the beating heart of Puppet. Beating because Puppet, it runs every 30 minutes. 30 minutes. It's always running to keep my nodes in check. It's not enough just to build the image. You got to keep it good. And for example, on this workstation, the one that you're seeing the screen of right now, you know, it's not something that I'm constantly reinstalling. I run Puppet on it, and so the same Puppet code. Here's the value, right? The same code that configures the image can enforce my desired state continuously. Post install. So write once, run everywhere. But this is just a Puppet module. It's a Puppet module, so if you're familiar with Puppet, you've worked with Puppet before, you know, you'll be familiar with what these directories are. You know, the main stuff is like the manifest. These are the actual Puppet code. For example, the main class that defines the kind of configurations that I want are here. For example, all these different parameters that I might want to set, different services that I want on my nodes, different system settings, you know, which do I want to auto login? Maybe I do, maybe I don't. Which desktop environment or window manager do I want to auto log into? Sway or Xmonad? That's just an example, right? The system D journal, like on these SD cards. Have you ever corrupted one of these running, you know, on your Raspberry Pi because it's just writing logs constantly or whatever else? That's what happens. You're constantly writing data. It kills these. Well, I turn that off. I turn off all those things that are constantly writing, like the system V journal. Um, well, I just make it volatile, right? So it's just in there. So just another example. The MTA. Do you want to use null mailer postfix? The VPN transport. You know, I've observed on when I'm tethered through uh, uh, Google Vi, they don't allow UDP VPNs, TCP. So you got to have options. You have to have the options. And so you can see these are all toggles that I've developed over the years, and that actually influence the behavior of this Puppet module. So beyond that, we deliver a base configuration, which configures a bunch of things, a bunch of aspects of the system, how it's configured, the time zones and the services and the fonts and I don't know, the Wi-Fi, you know, whatever. What packages should be on there. Everything that you would need to have a usable system is really defined here in the base. We do some conditional logic so that, you know, we're not, for example, building kernels until stage 2. You know, we're not building the bootloader because until stage 3, it just wouldn't make sense. So these are the ways that we optimize these builds, how we get those build times quick. And you can see here also in the base configuration, we deliver a configuration for Windows, for Cygwin, and that is an important design requirement for me. I have to have some sort of Windows support. But yeah, from there you can see, you know, all of the kinds of different manifests. So for example, I use containers a lot. Here's my container configuration. It says, these are the packages that should be installed. crun, CNI plugins, right? I actually got to fix that. It shouldn't be CNI plugins. I think it should be Netovart, and Podman. Um, and speaking of that, CNI plugins, Netovart, it just reminds me, this is my platform for learning about advancements of the open source world, right? So I would have no idea about Podman. I'd be using Docker if not for this project. The requirement for me to, for example, support ZFS, which is a core aspect of Nest. And Docker doesn't support ZFS, and Podman does. So it throws me deeper into the open source ecosystem in a way that I really benefit from, I think. But that's just an example there. So it's declarative. Can you imagine? Can you imagine what this would look like? It would be crazy to do uh, imperatively in Docker files, and then it would be useless post install, right? And so you're thinking, oh, I would do it in whatever Ansible or whatever. Uh, but ew, ew. What? This is a beautiful declarative purpose-built language for systems configuration, and you would use YAML? YAML's for data. And speaking of data, here's the data. Um, so I, for example, can use Hira here. This is part of Puppet for data management, right? Code is only as good as its inputs, and here are the inputs. So I can define, for example, that different package manager configurations. I want the latest versions of different packages because I trust them or I'm interested. I'm following the developments there. Um, I can set my kernel configurations across the board here. So, different networking configurations. Here's the frame buffer configurations, device drivers. But if I wanted a particular configuration for my node, for example, let's go to this platform section. Does Radxa Zero? Yeah, Radxa Zero. I want to support Ethernet over its USB host port on the Go host port. And so I don't want to enable that everywhere. I don't use it everywhere. It would just bloat the kernel, especially for something like this driver, which you want to build in so that it's enabled literally at boot, right? You want that network card to exist as soon as possible. And, you don't want to deal with kernel module loading that early on at boot. I want to know right away that this thing's connected. So yeah. Here's more examples. I don't want to enable Wi-Fi and everything. Because not everything has a Wi-Fi chip. My main workstation doesn't have a Wi-Fi chip. So it shouldn't be there. And I turn it off. I toggle it off on. Puppet. Like I said, this thing's it's good. It's fast. It's zippy. It's fat, but it is not capable of really reconfiguring itself and running an application, a workload, right? Alone, it can do it, and that's fine. But ongoing, I don't want to impact my workload with Puppet runs, which can be expensive. So I turn it off. I can do that. And instead, I just reset this from stage 3 every once in a while. Turn off FS cache. Define the bootloader, the DTP file. What do some other ones look like? Maybe my BeagleBone Black. This one's interesting because it's a 32-bit architecture. Ooh, 32-bit. And it runs ZFS, if you can believe it. We actually back in the architecture, because it's a more generic configuration than just a BeagleBone Black, we say for 32-bit nodes, we change the VM split. This is low-level stuff. We say we actually change the way the kernel allocates memory so that we can run ZFS on a 32-bit node, and it works great. But all of this is clearly separated: data, code, and that data is really looked up based on hierarchy, which we also declare right here in the same repository. There's no magic to it. The other thing we can throw into here are files. So Xorg, right? Here's my old Intel Xorg config for enabling tear-free video on Intel. So Bird is a routing daemon I've been playing around with to get BGP working for load balancing Kubernetes services. It's not important, but just a service definition file, that's fine. Contrary to that, we have to files, we have templates. So we can look at my Bird templates, and here's an embedded Puppet template file that takes parameters and can define my configuration based on those parameters dynamically. So that's really cool, a really useful feature of Puppet. It's very common to have slightly different configurations on different nodes. And so using templates to sort out the common set versus the differences is a very valuable tool for me. And beyond that, we have some plans. This is like orchestration, more of that imperative. I don't want to say imperative, more of a on-demand style of configuration management that I use to operate Nest. So I want to force a Puppet run. I want to force a kernel build. I want to force a reboot. I can do it centrally. And we'll take a look. So, I mean, there it is. And there's a screenshot of Nest within Nest. There you go. So how are we doing here on stage 3? How's my pipeline? That first rsync definitely takes a little bit longer, but yeah, you can see that green check there. We're good to go. It's done. And so what we're going to do is I have SD card reader. A bit there. Here, let's into my laptop. And for now, because this is still a new platform, I haven't made a new release of this of my CLI. I'm just going to use my development version. Let's say bundle exec bin nest install. Give it a help first. So I have a CLI. Nest has a CLI. What can this CLI do? It can do a lot of things. We can manage boot environments. This is a concept I borrowed from OpenSolaris and Android to an extent, B8M. And so we can do things like create, destroy instant copies of my operating system. So if I say nest B8M list right now, I have 2, A and B. I can say status. We are currently on boot environment B. the next environment, if we reboot, it will reboot into B. But I can create an instant copy of this operating system, call it test. You can see it issues some commands. Basically, it clones this boot environment, which you can see here. These different boot environments, A, B, and test. They are independent from my data, like in my home directory, home James, or my services, SRV GitLab, for example. They live outside of the boot environments. They're not affected by the boot environments. That's another way I can maintain this without losing my mind. So if I say list again, there it is. I can do things like mount it up, mount test, and mount. And there's my instant copy of my operating system. How cool is that? But I can do more with this command. What else can I do? So maybe I want to run something in that mounted boot environment. So I have this exec subcommand. And this lets you launch a shell or a command in a nest image. And that nest image can be either a boot environment, a mount point, a nest host image, or a container image. This is really, really cool. And there are a bunch of options that you can control how this works. But I can jump right into that test boot environment. There you go. I'm in a actual copy of this, and I can just do whatever I want, destroy it if I want. It's a clone, it's a copy. It's not a big deal. Of course, because it's tmux, I can do all the splitting things, and you can see the set of processes there. It's a container. There's nothing running. Other things you can do, X logo, yeah, like X works right through the container. So you can run applications from in the container, right? K, yeah. So like if I run K right, this is running in the container, right? I have just an instant clone of my operating system that I can experiment with and then throw away. And that's exactly what I'll do now. EADM destroy test. It's gone. But as I was saying, you can exec container images. So what if we say exec stage 1 as well, server? It'll pull an image in GitLab. The image that we just saw the build process for. Takes a minute. It's a big image. There it is. It takes a minute. There it is. Subsequent runs will be quicker, right? My tmux configuration was optimization, I'll admit, but this is a totally different image. I can run something here and throw it away. But this is great for development. But moreover, I could even run. I don't have the binaries here yet on this workstation. It's not powerful enough. But on my main workstation, I can run a alternative architecture image on my AMD 64 server using QEMU. It is emulated. That's another way that I can develop and experiment. But what else can we do? We were installing this SD card, which is here SDD. It's my 32 gig SD card. I can also say tmessage and see that it was the one that was the most recently connected SDD here, SDD. I have other things I can do. Well, install, reset, update. They're all specs of the same kind of thing. So we're going to install, say help install, see all the installation options. We can give it a disk. We can choose to encrypt it. Some other sort of debugging and other options. The installer kind of defines these steps: partition format, mount, copy, bootloader, umount, firmware, cleanup, and you can start and stop at any one of those steps. So if the install fails, you don't have to start from scratch, but it's usually not a big deal because the installations are very quick. So in this case, we see we have to give it a disk to install. We have to give it everything else is optional. Name is a host with a valid stage 3 image under nest hosts. Well, we better hope that our demo host is under there. So we say ls nest hosts demo. There it is. There it is. Just having this, as a plain old file system that's on NFS in this case, is so powerful. I can't write to it. It's protected. It's still a secure thing. It's just that I can interact with it without any special tools. And that's precisely what the installer does. So finally, let's install to dev SDD, my demo. And I am going to choose to encrypt it. I can give it a passphrase, but I can also just do a passphraseless. I think encryption is still valuable even without a passphrase because you can always add one later, but you can't add a passphrase to an unencrypted or a plain text or a clear text data set. So why not just have them? Why not just encrypt it? These things are fast enough. Even that BugleBone Black, that 32-bit ARM node, it's fast enough to do encryption. So just do it. There's no excuse for any removable storage device to have plain text data, because then you have to wipe it securely when you want to discard it. I just changed the passphrase and throw it away. Okay, so we see the installer, wiped the disk, ran SFD, partitioned it, created the Z pool and all the initial data sets here, including that initial boot environment A. We created a swap device and it looks huge, making an 8 gig swap drive on a 32 gig SD card. Now this is needed, as you see with the ref reservation. It's basically a fake volume that I use for Z swap or compressed swap in memory. It's actually faster than virtually any disk-based solution these days. And it's essential for running on these low memory nodes. I can run Nest in my smallest node is, it's Eagle Console. It's a Raspberry Pi 3. well, you can see up here, 350 megs. So yeah, smallest we can do is 350 megs. Swap here, 8 gigs. It's not, it's fake. It's just a space that the kernel can pretend exists for the purposes of swapping pages and compressing them and then putting them back in memory. But we'll return here and we see, all right, so you'd have settle, make the swap. That's not real. It's just Z swap, make a boot partition, file system, mount it, and then we copy. We literally rsync. We rsync the image to the SD card. It couldn't be easier. So I will return. Okay, yeah. All right. I was trying to think of what to do while this is installing. It takes these SD cards, they're so slow. This is why we try to make it as simple as possible. A straight rsync is about as easy as it gets. Why not copy? Rsync is faster. It's actually faster even than a straight copy over NFS. There's less network traffic. It preserves ACLs better than NFS does, and things like hard links. And it's important when it comes to updating. And so I think while this is running, while this is installing, it'll only take like 10 minutes. I will quickly show how we can use the CLI and these images, this concept of images to update the node. So earlier I showed you that big stage 2 build. Wherein we, compiled all these nodes. That was because I pushed a Puppet configuration that enabled the Ceph kernel module. That's a project I'm working on to do replicated storage for my Kubernetes cluster. I need the driver for it. That's not built in to the Linux kernel by default. So I rebuilt all of my servers in a couple hours. Is not a big deal. But I still have to roll that out to the nodes here. And so I thought, yeah, maybe we'll do it here for eaglet 6. This is one of my Kubernetes nodes. If I say KG nodes, that's kubectl get nodes. It's slow because they are slow single board computers. You can see all of my Kubernetes nodes. This is just one of them, a worker node, and it currently gzcat raw config. Currently, let's see, rep Ceph. Ceph. Yeah, it doesn't have Ceph. I don't know why I'm doing it as root. Let's not do it as root. Because that was just wrong. That's the other thing about Nest is I try to maintain a strict separation between my user and the system administrator, James and root, and I do. It's very strict. But I also want zero friction to move between these roles. Zero friction. I don't, once I'm logged in, if I've passed that ZFS passphrase, that should be the end of the story. It should just work for me. I don't want to fight my operating system. It drives me crazy when I use other operating systems, Mac OS, Windows, Ubuntu, commercial Linux distributions that just constantly nag you to allow. Are you sure? Are you sure? Yes, I'm sure. I ran this. I made this system. I made this. I trust it. It's don't bug me. All right. So when I want root, I type S, gets me root. Um, but otherwise, yeah, I do maintain that separation. So here, uh, I should really drain this node. I can't remember how to do that. I think it's kubectl drain node equalit. I can't see because of the zoom bar. I'm going to say like, no, I think it's just that. I don't know. I'm new to I'm yeah, there we go. Let's ignore daemon sets. I'm new to Kubernetes. I'm still learning. So it's fine. I mean, I don't. So there's a pod Kubernetes dashboard metrics. So it's so I have a pod on here that's doing. It's not too important. I mean, Kubernetes will work out. I just need to like reduce the load on here because this is a very slow server. I did not. I'm seeing Apache still. Why is that still working? It doesn't make sense. I just got to look at. I'm developing a plan for this. I just gotta. It's not ready yet. Destroy, remove worker, drain, delete empty dir data. I do that. And force. Go figure. I know. There we go. That's what we want. I just want to get the pods off here so that I can update this node um, without trashing the pods, basically. We'll just let it do it properly. Let Kubernetes move them. There we go. All right, so now there should not be any pods on this. You can see just right away in the top output here. It's quiet. It's quiet. How do we update nodes? Well, we can do it with the package manager. This is ultimately a Gentoo system, and we can use emerge and do all that, but it's the NestCLI. So we can either update or reset, and both of these are valid options. Update does use the package manager and calls Puppet. It results in the exact same configuration, but it is slower on certain nodes. useful if you have not yet worked out the the set of rules, the set of things that you need to filter out from an rsync to reset a node. So I've already defined these. I've figured it out for this node. I do not want to reset any of the Kubernetes stuff. You know, the Calico CNI network. I just don't want to reset it. That's state data, and it needs to be preserved across resets. This is all managed with Puppet. But that's how we can simply say nest reset. And here's another example of that frictionless systems administration. I didn't call sudo, and so the tool noticed that and was adding sudo to all of these commands. Another example of that was back when I was demonstrating oh, oh, it was in the CLI here. Back when I was demonstrating the exec, you know, all the BEADM stuff. Podman runs rootless, so no worries there. That's actually a really cool benefit of Podman is that I can simulate the effects of root as myself. Here is our sync. You know, it's getting there. It's getting there. So here's our install, I should say. The install of our demo server. It's getting there. You know, like I said, it takes about 20 minutes. What was I? Oh yeah, Eclipse. And okay, yeah, let's scroll back up because we missed it. We missed it. We missed it all. I was distracted. We missed it all. There it is. That's reset. Um, so you can see it destroys the previous boot environment, makes a new one. Sorry. And mounts it up and runs rsync. It runs rsync and it only copies things that changed. In this case, it's going to be timestamps, right? Because the images are built fresh every time. They're built fresh every time. And so to bring this running system into compliance with the image, yeah, it resets the timestamps. That's just part of it. It's not a big deal. It's a metadata operation. And because the boot environments are ZFS clones, this is a very lightweight operation. You see a lot of files being copied, but these are bytes. Bytes. And we can prove that. I say ZFS list are equals. We're going to get a lot of containers. So we're currently on A. So B represents the clone. And you can see the sizes here are identical, 2.2.5 gigs. But the amount of data that is referred to is much smaller. So on A, that's incorrect. Ultimately, what we see is you know, these snapshots, these clones are tiny, tiny, tiny. So here is that reset. And after we install this demo server, I'll reboot this and it'll show that Ceph is there. How about that? We are asking a lot out of this laptop right now. I'm recording, I'm doing I've got virtual machines running. I've got Chrome going, got GitLab running. um, got two Chrome windows going. Let's see how I can kind of tab these here. I'm just using my window manager. This window manager is based on Xmonad, but it is my own sort of design. All the colors, the styling, the fonts, and the automation that builds it as well. This is not managed by Nest. This is, again, that separation between user system administration. This is my stuff. This is not part of Nest. So if you're interested in what you're seeing visually, check out Dotfiles. It includes all the automation for things like Xmonad, and you can see, for example, that they are templates as well. So, for example, I don't hard code anything like color schemes or differences for different hosts, and I don't really want to work out how to do that in Haskell because Haskell is kind of a nightmare, especially when describing little differences between functions. It's like crazy. So I just do it simple, and it allows me to maintain like a consistent approach to customizing my dot files across different nodes. So on Hawk, this node here, I do want, if it's not Hawk, then I don't want to spawn Firefox when I go to desktop 4, which is it's music desktop that normally it would automatically launch. In this case, like YouTube music. And that's just because I don't want to use Firefox on this node. This is a virtual machine. It doesn't work quite as well as Chrome does in this virtual machine. It's fine. Nest gives me these options. I have options here. But all of these dot files are in turn deployed and maintained by Puppet. So there's kind of a connection between this and Nest, but it's a little bit not well defined, I'll admit. So some other things you'll find in here are, for example, my sway configuration. This is, let's see, also, again, I'm using the templating language to make these things, but GitLab will still pre-process them. So in a pipeline, it will literally process those with basically default values. So on hosts, on non-Nest hosts that don't have all those variables, I can just bam, blip this onto so on Nest hosts that don't have like all on so on non-Nest hosts that don't have all those variables, I can just throw it on this pre-processed repository, and maybe mostly just works. But yeah, sway config, this is like my Wayland equivalent to Xmonad, and it functions almost identically. It's an area of further development for me. I want to keep improving my Wayland support, but there are certain things that it simply can't do yet. Like you won't be able to see this, but like I can instantly move my cursor. You may not even see it. Here it is. Here's the cursor. And now the cursor's on a laptop that's behind this one. So I can control multiple nodes with a single input device. That's something that X is good at. Wayland is not by design. No, by design, and there's no getting around that. And so as long as X is supported and maintained, I'm gonna run X. It's like ultimately it has the same capabilities as direct rendering. That's what you want. You want high-speed direct rendering of graphical content, and through years and years and years of extensions, X has achieved it. And it's only that they want to simplify the design that Wayland came about, but it's not adding anything new to the equation. It's the same technologies. It's just put together differently. And I personally want to support and use it. I just there are certain capabilities that aren't there yet, and but I'm so happy that like I have this platform that I can build and experiment with. And so that'll be upcoming. Some other upcoming things, definitely. I've already ordered this. We're gonna build Nest for RISC-V. This is gonna be my new workstation. It's a 64 core, not very fast. It's two gigahertz RISC-V board, but it's the first like usable desktop level kind of RISC-V board, and this represents my chance to jump and build something new. And I'm really excited about that. I feel like Nest has all of the right pieces. For example, when I went to Bootstrap this new platform, and I did it in less than a day. There were lots of problems, but I have all of the right pieces. I have the U-boot forks. Believe me, I have the kernel forks. And I just quickly, like, I have these things. Amlogic. I can copy. I have the capabilities of integrating many different projects to build something coherent. And so when I see a new piece of hardware like this experimental piece of hardware that it doesn't even have EDK. It doesn't have firmware. It doesn't have firmware, guys. It doesn't have firmware. But I see that they have a basic porting of U-boot. Well, I mean, like, I can do that. I can, fork, and I have that, and then I have all the automation inside of Puppet to build those different variants. And I'm really just to prove that, I can look at my firmware here and different kinds of definitions for firmware builds, but you can see that here. The ability to define configurations, specify them per platform, and then build it. So I think I have all the pieces, and I'm really excited about building something, prettier, I'll admit, prettier than this. And that's, I think, going to be fast and fun. I've been following some of the controversy around the development of RISC-V, which is really interesting, particularly the vector extension, which was released in a lot of hardware units like this Softco. What's the chip called? SG 2042. Like, it was released with a draft version of the vector extensions, and like nobody wants to implement support for the draft extensions, but you can't buy hardware with the final version 1.0 of the vector extensions, and so people are hacking in different patches to the kernel and bin utility and the tool chains and the like to get it working, and they're realizing incredible speed ups as a result. So I think it's going to be a really interesting and fun platform. That's another future avenue. And yeah, we are also very much. I got to close this window. Very much getting into Kubernetes. And so my goal is I have all these plans, for example, for how to build a Kubernetes cluster. I have a number of plans here for managing a specific Kubernetes cluster, which I've called ARI. And so, for example, I can have plans here for how to deploy specific applications like my the static void log. If you go, why does Chrome do that? See, that's why I use Firefox. But here, this is my old blog. It runs on my Kubernetes cluster. My portfolio here also runs on Kubernetes. It's really slow. I don't know what the hell is going on, but they're slow single board computers. It doesn't need to be fast. It just needs to work. Um, that's fine. Nobody goes to the site. Nobody literally look at this. Nobody goes. Look, nobody goes here. There's been over 2 days. There've been 5 visits, and they've probably all been. Nobody goes here, but it has projects and stuff. And I host this on my Kubernetes cluster now. I want to get more into Kubernetes. I want Nest to be Kubernetes, cloud native, really, cloud first even. And to that end, I have Puppet configurations for a number of services that you might be familiar with, services like Plex and WordPress, GitLab, Bitwarden, all these things. And for the most part, they are, if we look at Plex, they are just deploying containers. And that's, I think, the way it should be. Apps should be, they should be containerized because apps can't be trusted. But if it's in a container, then it should be orchestrated. It should be managed by a container management platform, and that's what Kubernetes is. So rather than me saying, okay, on this node, you're going to run this container, I should say, this service should exist somewhere. And so what I've been doing is going through these services, and oh my God. See, that's the reason why my system here has slowed down so much is because we're in the final stages of the installation. And if I can switch over, oh boy. Yeah, it's slowed way down because I forget the final installation part does run Puppet. I'm just asking a lot of my server system right now. Oh, but what I was saying was I'm moving all of that into, Kubernetes. So rather than, saying run this container, I'm saying deploy this Helm chart, and maybe we have some, specific customizations, for a specific instance of that service, that app. We have a specific email address, or when I look at my various app configs, for WordPress, maybe I want to configure certain aspects who it runs as. How about that? So that's where I want to get to. So three kind of avenues of exploration: improving the desktop on their end, uh, introducing additional platforms, and experimenting with that new free open source hardware community. Continuing my path to my own self-hosted cloud. So here is our eaglet. This is the node that we reset. I see some hints that this might have worked in our rsync output. We see some new Ceph-related files, but because that was in another boot environment, yeah, we have to reboot. Boot environment B will be active on next reboot. I can confirm that with this PEADM status, and it will tell me, hey, you're currently on A. When you reboot, you're going to be on B. This is just like Android. This is very similar to Solaris 11, Open Solaris. So let's go ahead and reboot. And we have entered the final stage of our installation, finally. And this is where we install the boot. This we farm out to Puppet. Puppet has the knowledge of how to do this. And again, I do not want to replicate a bunch of imperative code. So to the extent that I can, we just call out to Puppet. And we do so in a container. This is actually using QEMU user. Okay, so this node does have the right binary. I just didn't. I think they all do. And we'll give that a few minutes to install. So this will come back. When this comes back, we'll log in and check that Ceph support. Meanwhile, let's look at some examples of where do I run Nest. I have some photos. So let's look. Hopefully I don't have anything too embarrassing here. I'm just gonna click on one real quick. All right, so here is my main workstation. It's it's a beast of a system. It probably weighs 50 pounds. And it has, I'm very proud of it. It's like 10 years old at this point. It has dual Xeon 2630 V2s, V3s that I overclocked to 3.2 gigahertz, 16 cores, 2 threads each core, 32 threads. It has, and because of the hyper-threading and the nature of this system, the size of it, I divide it in half and I let Linux have one set of threads and Windows have another set of threads. And so we have basically real-time hardware scheduling of 2 operating systems on one node. And I pass through this Quadro to Windows node, this Radeon something or other to the Linux node. And yeah, they just coexist, Windows and Linux. There are certain things that just don't run on Linux. And so I like to have Windows, and Puppet will run on Windows, configure a Cygwin environment, and deploy my Dotfile. It works basically the same. It manages my Firefox configuration like. So this is my main workstation. 8 drives there. Each of these is a RAID Z, with 1 parity drive, 3 data drives, and then these are joined together, concatenated together, and make a RAID 0. So this is basically a RAID 10. Familiar with it as 8 drives. This is about 40 terabytes. And yeah, I use it. I use it. Believe me, I use it. Believe me. Okay, what else do we run this on? So this kind of represents the pinnacle. This is the height of what Nest runs on, and I want to not replace, complement it with a powerful RISC-V workstation. So we'll have kind of this guy and that Milk 5 Pioneer providing basically server duties, routing, the Puppet, the yeah, kind of the main guys. What else do we have? Okay, this is my BeagleBone Black. I've had this thing since probably 2009, 2010. Um, I'm and I'll probably have it forever because what I love about this BeagleBone Black is that it is about as powerful as my first PC. My first PC from 2000. It's single core. It's low memory, 512 gigs. It's really hard to work with, and that's a good thing. No, it's not hard to work. It's actually really easy to work with because it's an open source platform or fully open hardware. That's everything, right? The BeagleBone Black. It's a challenge to work efficiently on, and I love it. So, um, and I will always have it just to prove that I can still run my operating system on something as powerful as my first PC. So what does this do? This provides Bastion access to my system and serial console stuff. So I can reset power on, power off, serial console, this node from this one. Nothing fancy. That's all I need. Each of these does kind of its own thing and does it well. And this gives you all that dust. It just sits there doing its thing. It's always working. Here's my Kubernetes cluster. So this is a Pine 64 cluster board running 7 Sopine ASICs. Yeah, Sopines. They're basically single board computers in a SODIMM, like memory card style interface. This board is really immature. This cluster board, it's very buggy. Like there's even a bodge job here that they did from the factory, like to get the eMMC working, and even still, it doesn't work at the full speed. I had to downclock it significantly to get it to work stable. Yeah. Just other things like you can't individually power any of the nodes. And so I hacked together yeah, this Raspberry Pi 3, and don't look too closely at this. It's probably all wrong, but basically I plug into the reset header of each of these nodes, and I can remotely using a bolt plan bolt plan show nest theory image node. I think that was the plan. Manage Eagle. Well, it's not too important, but ultimately I have a plan that just runs GPIO commands. It's wrapped up pretty nicely in the sense that I can issue a target and a power value off, on, reset, right? Um, so basically I've through Puppet and some hacking with some jumper wires, jumper cables here, hacked power management for my node. I've also um, got serial a console running to the first node here. And that goes into the UART of my Raspberry Pi, so I can get serial console access, which is important when you're developing a new platform. Nothing will boot correctly on the first try. Believe me, nothing will boot up from the first try, so you have to take advantage of these debug pins and stuff to actually figure out what's going on. On the front here, you can see, hey, that's one of these. That's one of these. It's the same thing. And it's plugged in, and it's getting power, and it's getting that Ethernet over USB. And this is ultimately plugged into the first node. And so this is getting power and Ethernet through this device. So it's kind of like a little parasite, but it's a way that I've been able to extend basically my cluster, my network. And I have these on a bunch of things you'll see in another photo. Really useful. Here's another board down here in a case that I use for building things and streaming and other experiments and just playing around. So see, here's my Kubernetes cluster. How about that? Right. Oh yeah, this was my my Raspberry Pi, my Raspberry Pi 400. This is you know, intended to be my Sway development workstation, you know, where I'm building that Wayland version of this desktop that you see. This board, this thing is so slow though. I've done everything I can to optimize it, and it runs pretty well, but I can't run a web browser in it, so it's not at any reasonable speed, to be honest. So I basically use it every once in a while to write some code, and it's fun, but I'm waiting on the Pi 500 basically, which should basically solve all my issues. And really, this RISC-V is going to largely take over the role of this guy here that's sitting on the desktop. Here's my main system, and they're all connected. They're all connected. Sound, they're all connected. So and here are a couple of ARM 64 build servers. These guys are the things that run those pipelines. Not big, they just sit there. Sorry. You know, they sit there drawing power from the Ethernet. I got a couple more parasites here. So these are getting Ethernet through this device. But, you know, if I ever shut these down, they still get network over Wi-Fi. They just switch. It's active backup. So power, Ethernet, and then, you know, if it network fails, it's fine. It'll connect over Wi-Fi. So I really like this solution. I really like these little boards. Cheap, extendable. Just plug them in. Just plug them in anywhere. And so that's it. So where else does Nest run? It runs in the cloud. It runs in Kubernetes. It runs everywhere. All really cute. So then, I think I saw, yeah, Eaglet was up, so we should be able to SSH in here. And one of the first things I like to do is run ops. This is just a little command that organizes my tmux windows. It launches an htop so I can see what's going on. Cheesy, yeah. Now I can look at my kernel config and see, there it is. CephFS is there as a module. I can probably load it. Modules, spell it right. How about that? How about that? Ceph is now loaded. I didn't build a darn thing on this node. I let another server do that for me. Again, in a mere hours, and you saw live here that we just reset this. And so I think we can uncorden this node, KG nodes, do this. I'm still new to Kubernetes, guys. I'm learning. Yeah, see, scheduling is disabled on Eaglet 6, and it's fine. If I like say systemctl status, everything's running, right? That's another thing you can check. SC status kubelet is running. Cryo is running. Bird is running, right? IP route show table bird. You can see my routes to my redundant routes to my highly available Kubernetes API server. How about that? Gordon node. Gordon. Yeah, I'm Gordon. UK, I'm Gordon. Equal 6. AG nodes. And almost instantly, let's see something. No. But as I go through and update the rest of my nodes, do the same thing, drain them, reset, reboot on Gordon, nodes will pods will be just shuffled across, and the services will stay up, which is the way it should be. There's my Eagle cluster, part of my Kubernetes cluster. Right. Last thing I'll say about this. Yeah, I just described 4 processes that I have to repeat, right? Drain, reset, reboot on Gordon, right? And that's a puppet plan. That's a puppet plan all day. YAML plan, command, reboot, command. That's what I'll do. Have all these tools available and they work for them. And that's a beautiful thing that messed. Last thing, CLI. If we look here, Puppet ran, it managed the state of the bootloader. I don't care what it did. I forget half the time what all this stuff does, but rest assured it did it correctly. And then we install the firmware, which is another thing. Like, really great to just be able to DD it directly from the host file server. That's fine. Again, these builds are defined and configured and managed by Puppet. So ultimately, all we have to do is install it to the right place, which is a one-time thing. So then let's go. Here we go. Here's the SD card. Here it is. Reach a board. Put it in. Here we go. One end in here. One end here. There's the laptop. You should see, little LED. And give it like 2 minutes. 2 minutes to boot. No SSH. Do I need more? See, it's self-identifying as an Ethernet device. That's how I know it booted. That's how I know it booted. Because it's built into the kernel, that Ethernet driver. That's how I know it booted. I'll connect it to Linux. If I connect it to Linux, just interesting to see. Boom, I have a new device. So that's an aspect of how these worked. Really, ultimately, we're going to rely on, in this case, because this node, this workstation is not configured as a bridge. We're going to rely on this guy here, which is the Ethernet chip, uh, Wi-Fi chip, Wi-Fi module, and then let's see, right there is a little antenna, which is kind of neat. So if I say ping demo, what do you think? What is going to look? This doesn't work. I don't know what I'm going to do. So unfortunately, I'm going to put this down. Trust me that this thing is running. Unfortunately, because I now poisoned my DNS cache with a bad lookup, I have to say flush. I am a little concerned it's not maybe booting. It's because of the hmm, I should just plug it into straight power so I'm not the Ethernet bond shouldn't matter. Shouldn't matter. I'm a little worried. Damn it. It's supposed to just work. All right, we're gonna try just plugging it into straight power. I have two cables. This one's just straight power. I know it loaded because obviously we see the Ethernet device. So it's just why didn't it ultimately connect to my network? And I think it was because it was trying to connect through that network. But yeah, that could be it. That could be it. Seems unlikely. See, and if this doesn't work, like I'm stuck here because I don't have the debug tools down here. And I wouldn't sit here and debug this. I mean, this should just work. Like I've built 5 of these in the past 2 weeks, over and over and over again. Like this should just work. I think it was just because I'm plugging into a foreign computer. There it is. See, look. See, did you doubt me? Did you doubt me? Come on now. Come on. Let's go. Just like that, we are now on this. We are on this board. So again, I'm going to type ops because Puppet managed all my dot files for me. Everything that I expect should be on here is on here. Just prove that I am on this. Here, let's say your name, LSCP. How about that? Let's see. We have our 4 Cortex A53s at 1.8 gigahertz. We have our 4 gigs. 4 gigs. It's not even as close. It's basically 3.5. How about the boots? Boot successful. We see running 0 failed jobs, right? How am I? How did I? Just for the reference here, the cable issue aside, just for reference here, if I plug this in anywhere in the world with internet access, I will be able to. How is that possible? Well, it's VPN, which I disabled on these nodes. That's right, because I'm connected to the security. But um, typically, like the workstation I'm on here, we look at its interfaces, and it's all over VPN. But hey, how about that? We just built a brand new board. Now, all right, you're like, what can I do with this? Well, I just showed you a bunch of things you can do with it. But ultimately, you have a computer that's running your operating system, your configuration, your software that you built. You put this thing anywhere. Put it in a cupboard. Put it in your garage. Put it next to your TV, and then plug things in. You have USB-C. You can plug devices into it. You have an HDMI. You can plug it into your TV. You can watch videos, and you have all these GPIO pins, right? I showed you a picture of jumper wires doing things, right? Plug it into different devices. This is your IoT solution. I wanna like plug this into my garage door. I want to get rid of that stupid freaking um, vendor app that I have to use to open my garage, which hangs like you know how frustrating it is when you come home and you want to get into your garage and you have to open an app that then shows you advertisements and only works half the time? Or would you rather plug in a $30 single board computer with an operating system that you built and trust completely, and just plug in some wires and then issue a couple of commands um, that could operate over a web service, right? That you authenticate to, right? It could be very simple, and it's enabled. It's enabled through IoT devices like this, Internet of Things, and this is how it happens. A cheap computer running a full operating system that you can control. So, all right, this has been a lot more than I originally expected. It was kind of rambly. I really just wanted to show off some of the core features of Nest. I didn't even touch on half the things, like all of the unique software and service integrations that Puppet is doing for me. I didn't even touch on, for example, uh, my Puppet dashboard. Like I have this whole dashboard that I can see the state of my nodes. I can look at my inventory, see, which ones are out of date, and see all my Nest servers, Windows 10 servers. I got a couple of them, different versions of Puppet. Look at that. I'm all on Puppet 8. Hey, let's go. Um, but like I have lots of tools at my disposal. I didn't even touch on half the things I do with GitLab CI to make my life easier, but all of this is constantly working to enable the kind of projects that I want to do with the kinds of hardware that I want to deploy. Arch doesn't run on this. Ubuntu doesn't run on this. And if you buy this, you're going to be given some sketchy image from some Chinese vendor. I wouldn't touch it with a 10-foot pole, but my own self-hosted, self-compiled, built 100% from scratch OS on whatever board you want. Let's go. All right, so this has been a quick look at Nest. If you have any questions, thoughts, comments down below, I'll answer them. This is just a playground for me. Like ultimately, I want to get this to a point where I release it that is replicatable, replicable, um, in the sense that you can bootstrap a new Nest cluster on your own environment with your own credentials and passwords and this and that. Yeah, I didn't even touch on stuff I'm doing with the EM. It's incredible stuff. And mostly it's driven here out of our Puppet configuration. And so this is where you want to to begin your inquiry, if you want to look into any of how this is set up, ultimately this is my playground, and I'm happy to keep it that way. I don't answer to anyone but myself, and that's great. I, I do this also for a living. I'm a professional systems engineer, and um, I take enough requirements, design requirements from other people that to have a project that is 100% my own is it's not something I'm going to give up. So uh, eventually I want to release this, but if only to say that it's an actual real distribution. But I think you can see all the tools are here. It's built 100% from scratch using my own configs. Uh, from literally the firmware up, there's nothing on here that I didn't compile except for the firmware on that chip. So I'll do some more, I think, demos here on Nest. I think there's more to get into, but let me know what you want to see. Let me know what you think, and I'll see you next time.